Hello team, in this video we're going to talk a little bit about data center pods, which we've seen is the building block for data center these days. So the previous approach to building data centers was to store servers in racks and then connect the servers in the rack to a switch that usually resides on the same rack. So we call this switch the top of rack switch. It resides on, might be on the bottom or the top of the rack, and then all the servers on that rack connect to that network switch. And the rack might have one switch or two, depending on how much bandwidth or redundancy you want. Then these racks would be interconnected with an aggregation layer, which are switches with higher bandwidth ports. Like if the top of rack switch has 10 gigabit interfaces with the servers, they might have 40 gigabit or 100 gigabit interfaces with the aggregation switches. And then depending on how big the data center is, the aggregation switches might then be connected to core routers that's going to route the data between the aggregation switches. So if server in rack 1 talking with another server on rack N might go through multiple switches to exchange data. A more modern approach to looking at data centers is to think of them as built out of pods. So here we have pods on the bottom, and these pods, they have several racks with many servers inside, some internal networking, and then they connect to this routed core. So the routed core might have multiple layers like an aggregation, a spine layer, core layer, but we don't usually talk about these specifically. So here, just drawing like a routed core network that interconnects all of the pods. So the main shift here is how we think about data centers. So we don't think about individual racks or servers. Now we think about pods, and expanding a data center basically entails adding pods to it. So a pod is built as a unit. There's no thing such as a half pod or partial upgrades to a pod. So you build the whole pod as a unit, you deploy it as a unit, and then you manage it as a unit. And when the pod is outdated or it's past its replacement date, then it's decommissioned as a unit, and then you basically put another pod in its place. So there are no partial upgrades to pods. And pods might evolve over time as you upgrade processors, the amount of RAM on the servers. So pods might have generations. So you might have pod version 1 built in 2015, and then pod version 2 that was built 2017, pod version 3 2019, and so on. And then a data center might have multiple versions of pods, older ones and newer ones. So pods have internal redundancy for resilience, and failures in a pod ideally do not impact other pods. So they might impact the applications running on the pod, right? If an application is running on multiple pods and one of the pods failed, then that application might be failed, but failures inside the pod should not impact another pod. A pod can also be seen as a unit of computing resources. So a pod can provide predefined capabilities and interfaces. So developers and operators might have expectations on what a pod should provide. For example, a pod has compute capacity, some storage, and internal networking. And these capabilities might vary between pod versions or between different deployments. For example, we can have memory optimized pods with servers that have a lot of memory but not that many CPUs. We can have storage optimized pods with a lot of disk space or SSDs. And we can have compute optimized pods that have less memory but a lot of CPUs. So we can make these trade-offs, and then users, developers and operators get these expectations of what a pod can do. The internals of a pod may vary as the designs advance. Like I said, we can upgrade CPUs on a pod and then we increment the version number. We can design more efficient power distribution mechanisms, reduce power consumption, and so on. But importantly, the interface, the expectations that people have on pods should remain stable. If this is true, then applications should still run even when operators upgrade a pod to the next generation. And of course, what goes in a pod is a very important design decision. How much disk space we should have, how much bandwidth in the internal network we should have. So designers need to think about what applications will run and what capabilities we should add to a pod. Pod sizes vary significantly, and there are some considerations that go into deciding how big pods should be. So in blue here we have considerations that motivate smaller pods, and in red considerations that motivate larger pods. So one motivation for smaller pods is incremental growth. So if pods are small, then when you need additional capacity, you can just buy a new pod. It's not going to be very, very expensive, and then you get additional capacity and you can expand in small steps. If pods are very large, then you have to buy a lot of compute. Then if you don't have a lot of extra demand, you might have some utilized resources. Another consideration is the impact of failure. So if a pod is very large and a problem happens inside that pod, you're going to lose a lot of compute capacity. If a pod is small and there's a problem inside that pod, you lose some of your compute capacity, but you probably have many smaller pods, and then you might be able to move some of the applications running on the failed pod to other pods. For example, considering that servers these days run 25 virtual machines and we have pods with 16 racks, so that pod might be running on the order of 16,000 virtual machines, which is a lot of virtual machines to lose when the pod fails. Another consideration is management. Smaller pods are easier to test, manage, and repair. So that's just, the day-to-day operation of smaller pods is easier than bigger pods. And one consideration that argues for bigger pods is just compute capacity. So if you have bigger pods, each pod can run bigger applications. If pods are small and we want to run very large applications, we might need to spread applications across multiple pods. And this might complicate the design of the application and put additional strain on the core data center network. So usually enterprise pods vary between 12 and 16 racks, but of course smaller and bigger pods exist. For example, Facebook's Altoona pod has 48 racks. Going back to our data center figure, so this is a data center built out of pods, but I've expanded the internals of pod 1 so that we can have a look of what goes in the pod. So the pod has multiple racks. It will have top of rack switches on each rack, and then so here I drew one switch per rack, but there might be two, and then these switches might be connected to a aggregation layer or spine layer inside the pod to communicate between racks, and then these spine switches will connect to the core network of the data center. So there's some internal networking inside the pod so that applications can run on servers that are located in different racks. The topology of the network inside the pod varies. It depends on how much resilience we want. For example, if we want a lot of resilience, we might have two top-of-rack switches and each rack connected to two switches so that we get two links to each server. And also how much bandwidth we want between the servers.